Greetings, everyone. Welcome back to College Algebra. Time to talk about combinations of functions. And really what we're doing here is just learning some of the language and the symbols that we use with that language in order to create and work with functions that are being combined. So what we have here are the naming schemes and the way that you're supposed to read them. I know it looks like we're just saying a bunch of the same stuff over and over again on both sides, but you need to look at where the parentheses are and then realize what it is the goal of that particular formula. Okay, so for example, I have a function named f plus g of x. So x is his input, right? And it happens to be equal to the addition of a function named f of x and a function named g of x. Okay? So they look the same on both sides, but really what's happening is on the left-hand side, it's how we're naming a new function. And then on the right-hand side, how that new function is being created. Okay? So the scheme should be quite obvious. What's going to happen is they're going to give you 1, 2, 3, 4, whatever functions, and then you're going to have to create a new function based on the way that the name of the new function is given. And then on top of that, all of the questions that might be asked or analyzed about a function from before still matter now. They still are fair game at this point. So what can happen is they can ask you to find fg of x, let's say, but then they can also ask, what's the domain of fg of x? What is fg of 1? What is fg of 7? Right? All of the things that you would normally ask about a function still are valid because we're creating a new function. Okay? So we're just analyzing a function that is created by combining other functions and then the consequences that come from that. Okay, so let's get a few examples here. I have a function a of x, 3x squared plus 7x minus 4, and a function b of x is 2x minus 10. And I want to start by creating b minus a of x. So if I'm going to create b minus a of x, all that entails, in fact, let me do it this way. All that entails is me taking function b and subtracting function a. You don't actually need the parentheses on the function b part here. I'm doing it for aesthetics, right? The way it looks. So at this point, you need to be able to combine and just simplify things. And it is important that I put the parentheses here because I do need to distribute this negative. So I'm going to go ahead and do that, and I'm going to combine like terms. So notice I've got a negative 3x squared. I have a negative 7x plus 2x. And I've got a positive 4 plus negative 10. Okay? So I've created the new function b minus a of x. Next, ab of negative 2. There's a couple of ways that you can approach when you're asked about a function value of a combo function. Okay? One way is I can just go straight up the way of create the function, plug in the value, right? I need to have a function named AB so that I can plug the value negative 2 into that function. Or the other way is I can actually do A of negative 2 and B of negative 2 and then multiply them. Okay? So it really doesn't matter which way you do it. I'm going to do it the first way. So I'm going to create AB of x first. AB of x just means that I'm going to multiply 3x squared plus 7x minus 4 times the 2x minus 10, like so. Okay? At this point, I could leave it like this, or I could FOIL it out. It just depends. Right now, I'm noticing that all I need to do is do this one function value, and that's all the analysis needed for this function. So I don't really want to go through a lot of other work for just this one plugin. So that's all I'm going to do. I'm just going to start by plugging in the -2 now. That's just going to be 3 times -2 squared plus 7 times -2 minus 4 times, I'm using brackets so that they don't get confused with the parentheses here, 2 times -2 minus 10, right? The brackets don't have any extra meaning there. I'm just using them to lessen the confusion between the symbols. Let's see. So AB of -2 is equal to, I've got 3 times 4 plus 7 times -2. So that's 12 minus 14 is -2 minus 4 is -6 times, that's going to be -4 minus 10 is -14. So AB of -2, negative times negative is positive, and I've got 60 and 24 is 84. Okay? So notice I could have just plugged in -2 to each function individually. That's kind of what happened. Or I could have FOILed this all out, right? Multiplied every bit by every bit and simplified it, and then plugged in -2. You would have come up with the exact same answer. Okay? Domain of A over B of X. Now, this one I wanted to bring up because especially the domain can change a little bit when you bring up the division combination, because if there wasn't division before, then there is one now, and that could cause some division by 0 difficulties. Okay? So the domain of A over B of X. First of all, let's create the function. That's going to be 3x squared plus 7x minus 4 over 2x minus 10. All right, well, any new simplifications in there? Anything that I can bring out? Not really, right? They're not anything that I can reduce very quickly or easily. And there's nothing that's already ready to simplify between the numerator and denominator. So I'll just leave it in that format. And what the analysis of this one is they want to know the domain. Okay, so I'm going to look at it and say, well, everything at the top is all good because there's no square roots and no weird divisions. But then they got the big division bar, and this guy can't be 0, right? So what number, when you plug in the x, would 0 this out? Well, you could set it equal to 0 if you don't see it right away, right? If you don't see it right away, just set it equal to 0, or rather not equal to 0, right? Because that's what we don't want. And you could solve it. X can't be 5. So then my domain for this function would be that x is an element of the intervals from -infinity to 5 union 5 to infinity. Okay, so with all of the plugging in and the finding of the domains and things like that, there's really not anything new as far as the questions that can be asked about a function. Okay? What's different here is you need to be able to read the combination of symbols and what they mean, and the gravity of what they're asking you to do. The fact that we are creating a function and then doing some sort of analysis on it, plugging in points or finding domains or just finding the function altogether. Let's squeeze in a few more examples of function combination analysis, just to give some variety here, okay? Let's do the domain of f plus c of x, the domain of g times c of x, and the intercepts of f divided by g of x. Okay, so I've got these three functions here, and we're going to do these different combinations. So first, let's figure out f plus c of x, right? Let's write down what the function is. F plus c of x is equal to the square root of x plus 4 plus the square root of 9 minus x. And as far as square roots go, there's really not much I can do to combine those. So then what is the domain going to be? Well, I have to make everybody in the function happy before we can have any calculating going on. Okay? So if I have two different functions working together to make another function like this, I need to figure out the domain of each piece, and then I need to figure out if there's any places where they meet. It's kind of like having two kids in the back seat of your car that you want to reward by going out to eat, and you ask them where they want to go, right? And some of the kids say McDonald's, Taco Bell, and Rally's maybe, and then some of the other kids say McDonald's, Burger King, and CC's, right? Well, since McDonald's is the only place that they cross over, you know, if you're trying to reward them, you're going to pick the place where it'll make them both happy at the same time. Okay, so it's kind of like that. I've got a couple of things going on here, and I need to look at both of their domains and make sure that I've got a interval of x values that can make both of them work, right? Now with polynomials and some of those other functions like in the last scene, the domains are pretty much going to be everywhere, okay? That's why I threw the radicals and the rationals in here, because we can talk about some domain restrictions. All right, so the x plus 4, remember, to do his domain, I have to set x plus 4 greater than or equal to 0. That's how we handle a square root. Take the inside, greater than or equal to 0, solve it. I get x is greater than or equal to -4 for his domain, right? Okay. Over here with the 9 minus x, same thing. He's in a square root, so I have to set that greater than or equal to 0. Then I have to solve. So I will add the x and then write it in a better format. X is less than or equal to 9. Okay. So that's two very different types of intervals there. One of them is a left-facing, the other is a right-facing interval. And I can only pick numbers that make both of them work together at the same time. So you got to think for a second, do those even exist? Well, sure. If I put up a number line, or, well, just an x-axis, if you will, 9 is over here, and -4 is over here. I was told by this guy that he needs to be greater than or equal to -4, okay? So I need this direction here, greater than -4, but less than or equal to 9. So for this guy, he could only be less than or equal to 9. And I can actually leave them both bracketed because the endpoints are included in both, okay? And notice they will meet up. So then the domain of this guy is just the intersection there where it makes them both happy. X is going to be some element of the interval from -4 to +9. Next, domain of g times c. So let's create that function. gc of x is equal to, I'm just multiplying this fraction times that radical. And don't forget, the radical is technically over 1, right? I can think of this as the whole thing over 1, and I'm just going to multiply them like fractions. So what that's going to give me is x plus 1 times the square root of 9 minus x divided by x plus 2, like that. Now, of course, if there was more to simplify, I would, but there's really not much. I don't want to distribute that radical. It would just make it messy. I'm just going to leave it in that format right there. Alrighty, so that means that what I'm going to do is I'm going to look at each individual piece and see if there are domain things that I need to include. All right, well, from the last problem, we already saw that this radical piece right here has to have a domain restriction where x is less than or equal to 9 only. That's an interval from negative infinity up to 9, right? That's this guy. X plus 1 is fine with everything. He has no exceptions whatsoever. I'm not worried about him. X plus 2 also has no restrictions, but he's in a denominator, so I can't let him equal 0. So for this guy, x plus 2 can't equal 0, which tells me that x can't be negative 2. And it just so happens that negative 2 is a part of this set being less than or equal to 9, because negative 2 is less than 9. I need to make everybody happy. I need to be able to mix these two together. Okay? So this is what's happening. Again, imagine an x-axis, right? Imagine an x-axis where 9 is here and negative 2 is somewhere over here. My first bit right here is telling me that I can be okay with bracketing the 9 because of the equals, and he's good with everybody less than that. Everybody in this direction. This guy says, I'm okay with anybody except negative 2 only. I can't have him. So as soon as they get here, they have to both agree, okay, we can have all of these people to the left of 9, but this guy says he can't have negative 2. So I'll have to leave a big old gap right here where I've cut negative 2 out. So it's actually going to be two separate intervals, and negative 2 is sort of the cutoff here where I'm leaving just that one hole there. Okay? So the domain here is going to be that x can be an element of negative infinity to negative 2 union negative 2 to 9, like so. All right, and the last one, intercepts of f over g of x. So let's create the function f over g. I'm going to do this one piece at a time, one step at a time here. Here's f. That's the square root of x plus 4 divided by, and I'm going to use the long division terminology here so that we can see it, g, x plus 1 over x plus 2. Okay? Now I need you to keep in mind that originally the domain of f is that x can only be greater than negative 4, right? Because of this guy right here, x has to be greater than or equal to negative 4, right? And over here, x cannot be negative 2. Okay? So I've set up the function, and this is sort of like the baggage that these people are bringing into this relationship. Okay? That's his baggage, that's his baggage. We have to find a way to make both of those things work together in one household, basically. Right? I can simplify this right now. I could say f over g of x is equal to x plus 2 times the square root of x plus 4 divided by x plus 1. Now, how did I get that? Well, remember, when you divide by a fraction, you take the reciprocal, you flip it, and I just multiply. So what happens is the x plus 2 ends up in the top. I multiply by the square root of x plus 4, and the x plus 1 ends up in the bottom. As long as you remember that both of these things put together still make up the domain. Okay? It has to be this way. Plus anything extra that comes after the simplification. Notice, after I've simplified, right here, that x can't be negative 1. So, this is what's happened. These two functions have come together in this relationship. They've brought their own baggage. And then their relationship together has its own extra baggage to consider. Okay? Now, I didn't ask for the domain of this, but it's a good idea to write down the domain of one of these as soon as you start into it. Okay? So imagine your number line here, my x-axis, and let's see, let's put on it -1, -2, and -4. Okay, those are the three numbers in question here. The -4 says I can have everybody greater than him. He's okay with that. So I can bracket here and I can shade everything this way. But both of these guys are saying, okay, but I just can't have this one number. I can't have -2 and I can't have -1. So right here at -2, it's cutting out, and right here at -1, it's cutting out again. Okay? Now I know -1 wasn't originally part of the restrictions, but because of the way they're combined together, right, it's causing that availability that if you put in -1, you get a division by 0. The -2 and then the greater than or equal to -4 came with them beforehand. Now their domain put together is everywhere x is an element of bracket -4 to -2, union -2 to -1, union -1 to infinity. I know it's a little crooked there, sorry. -1 to infinity is that last bit. I'll just make some more space here. X is an element of bracket -4 to -2, union -2 to -1, union -1 to infinity. Okay, so we just need to keep that in mind whenever we're solving this here. Okay, it asks for the intercepts. So let's start with y-intercepts. Remember, y-intercepts are anywhere that x is 0. Is that in the domain? Sure it is. I can have x equals 0. It's in that last interval over there between -1 and infinity. Okay, so to have x equals 0, all I'm going to do is evaluate f over g of 0, because that's where x would be 0. So f over g of 0 would be 0 plus 2, which is 2, times the square root of 4 over 1. Right? What is that? F over g of 0. Square root of 4 is 2, times 2 is 4, over 1 is 4. So here's my y-intercept right here, plugging in a function value. Next, let's find the x-intercepts, or intercept, or whatever. It could be plural, it doesn't have to be. That's anywhere y is 0. Now remember, in a function, to do y equals 0, then what I'm actually solving is where does f over g of x equal 0? That's what I'm actually doing here. So then I'm going to have to solve this equation. 0 equals x plus 2 square root of x plus 4 over x plus 1. Okay, well, there's a couple of things here. I can multiply both sides by x plus 1, and anything times 0 is still 0. Like so. If I just multiply both sides by x plus 1, it eliminates here, and then times 0 is still 0. You find that any time in a fraction. The fraction can only equal 0 if the top equals 0. And that's pretty much a consequence of that. Now, from your factoring sections, you should recognize that this is something that's multiplied, factored out, and equal to 0. I can split it. This is telling me that either x plus 2 is 0 or x plus 4 is 0. Wait a minute, where'd the square root go, Mr. Simon? 0 squared is 0, right? So the square root has no bearing when it's equal to 0. So I'm getting x equals -2 and x equals -4 are the places where this thing is 0. But wait a minute. Look, -2 is not allowed from the domain. So I can't have this one. That's not going to be a x-intercept here. X equals -4 is included in the domain. So that's an intercept. In other words, f over g of -4 equals 0. And there's my other intercept. Okay? So there's some examples of finding domains and plugging in function values to these things. Now we need to talk about another type of combining that is not using one of the normal arithmetic operations. It's something that only functions can do. We call it composition. And basically the idea is plugging one function in as the input of another function. Okay? It's symbolized with the little circle like that. The little circle like so. Okay? And I know it looks like it says fog, but the circle is not an O. It's not on the same line. It's in the middle. And that's just the operator for composition. The meaning, as you can see, is to plug one function as the input of the other one. Okay? So if I have two functions, f and g, okay? F of g, what I do is I start off with a basic f function. F is the outside one, you see. G is the one I'm going to be plugging into f. So I start with an f function, but I didn't use x's this time, right? Think about it for a second. The function doesn't actually have to have x's in it to be the function. It just has to have a spot to put in inputs, right? So this is what I do. I write down a basic f function that's waiting for input, right? 9 something squared, 5 times something, and then plus 3. That's the same thing that this is doing. We just use letters to sort of hold that spot in line, if you will. But now I'm using big blank spaces, okay? But then what am I plugging in this time? I'm not plugging in x. I'm plugging in g of x. So in each of these blanks, where x used to be, I'm putting a 4x minus 7. And then you would want to simplify from there, right? I would multiply out everything that I could. I would have 9 times 16x squared. 28 and 28 is minus 56x. And then plus 49, because I had to do 4x minus 7 times 4x minus 7, right? FOIL it out. This is still here. I can use my distributive property. 9 times 16, 90, and 54 is 144. X squared. 450 plus 54 is 504. X. And then let's see, 450 minus 9 is 441. Right? Plus 20x minus 35 plus 3. So f of g of x is the way you say that. F of g of x is 144x squared. I've got minus 504 plus 20, so negative 484x. And then I've got 441 minus 32. So let's see, 441 minus 31 would be 410, so plus 409. Okay? So there's f of g of x. Next, g of f of x. Same idea, right? I'm going to start with a generic g function, which is for something minus 7. But in for that something, right? I'm not just putting x, I'm putting the function f now. So that's 9x squared plus 5x plus 3. Alrighty. So g of f of x is equal to 36x squared plus 20x plus 12 but minus 7, so plus 5. Me multiplying these out was to make sure you realize that f of g of x is not the same as g of f of x. In general, composition does not commute. All right, swapping the order on these very rarely gives the same result. In fact, there's only one important time that it does. When you swap it, it does give the same result. We're going to talk about that in the next section with inverses. It's a very small case. Okay. One more example real quick before we get to the big examples. G of g. Notice I can compose a function with itself. I have the g function 4 times something minus 7. And then what I'm composing it with, I'm plugging in another g function, like so. In fact, the ability to compose a function with itself over and over and over and over again is the major basis of a branch of mathematics called chaos theory, basing it on compositions of the same function over and over again to see if it causes chaotic behavior or not. Okay, so g of g in this case of x is equal to 16x, and then I have minus 28 minus 7, so minus 35. So let's finish up with a few more examples of some composition of functions and the analysis of what those make. Okay, so I've got some functions up here for us, a, b, c, d, and p. Okay, and then I'm wanting to find the domain of the a of c function and the domain and a function value for the b of p function. Okay, here we go. So the domain of a of c of x. First, let's create a of c. So I have a of c, and what I do is I set up a generic a function, which is the square root of 9 minus something, right? Here is the generic a function, and then what I'm going to be plugging in is the c function, the square root of x plus 4, like so. Okay, so then the parentheses are kind of unnecessary at that point, and then this is the setup of that function. If there are any other simplifications from here, this is the time that you would do them. Okay, but in this case, there's nothing else to square, to combine, or to simplify, or anything like that. I simply just have a radical inside of a radical. You know, as yucky as that looks, it's actually not too bad as far as functions go. All right, now let's talk about how to get the composition domain. Okay, whenever you have the domain of one of these functions, you have to remember that whatever the inside function is, in this case c, is going to bring along any baggage, right? Brings domain baggage. I'll put baggage in quotes. Right? Whatever the inside function is here, whatever the function being plugged in, it directly brings whatever baggage it has with it. Okay, and here's a prime example. You can even see right here, as soon as I were to plug in an x value for this function, the whole composition here, the first thing that it would hit is exactly the c function. Okay, from earlier we've already seen the domain of one of these functions, right? The square root of x plus 4. Just this piece alone, right? C of x domain was that x had to be greater than or equal to -4, right? Because of this square root right here, we know that x has to be in accordance with greater than or equal to -4. Okay, and we got that by x plus 4 has to be greater than or equal to 0. However, we now also have to obey the bigger square root, which didn't exist before in the format that you see. Okay, it's the newly, well, it would have been simplified had we had any steps, but it's the newly formed conjunction of the whole thing. It's no longer just the a function, right? It's not just the square root with the 9 and the minus. There's something more complicated here, okay? But in general, anytime you have a square root, the way that you find the domain is you take whatever's inside of it and set it greater than or equal to 0. So in this case, I have 9 minus square root of x plus 4 has to be greater than or equal to 0. And then we just need to go about solving this particular inequality. I can actually do this one directly because the square root, as we'll find out later, is one of these one-to-one operations that we already have. And therefore, it's not going to cause me any duality problems with the greater than or any inequality. So what I'm going to do is I'm going to add this over right here. I'll have 9 is greater than or equal to square root of x plus 4. Then I'm going to square both sides. 81 is going to be greater than or equal to x plus 4 after I've squared both sides. And squaring both sides doesn't change the inequality because it doesn't bring in any extra negatives or anything. Then I'll subtract the 4 from both sides, and I'll get that 77 has to be greater than or equal to x. Or in other words, if I write it in the more readable format, x has to be less than or equal to 77. Okay? So this has to be true for the whole function by itself. And then because of the way this was formed, you always have to bring the inside function's domain as part of the restriction. Now sometimes the inside function may not have a restriction, but this one did, right? C of x brought with it the fact that the domain was already restricted to being greater than or equal to -4. But this particular square root in the whole thing would not work if you plug in a number that's bigger than 77. X has to be less than or equal to 77. For example, if I were to plug in 78, right? Plug in 78 right here. 78 plus 4 would be 82. The square root of 82 is something bigger than 9. So if I do 9 minus that, I would get a negative number, which then this outer radical would have to square root that negative number. It wouldn't work. All right, well, putting all this together, my domain has to make both of these happy. It has to be bigger than or equal to -4 to make the inner square root happy. It has to be less than or equal to 77 to make the outer square root happy. I'm putting both of those together, and my domain is going to be x in the interval from -4 to 77 would be the domain of that function. Now, next function, b of p of x. I want to do the domain of this, and I want to talk about a function value and the couple of different ways that you can get it. First, let's create the b of p function and simplify it. So b of p means that I'm going to take the b function in a generic form, right? The b function is something plus 1 over something plus 2. And it's the same something in both cases, right? Right. So what am I plugging in? The p function. That would be 3x over x minus 7 and 3x over x minus 7. Before we go any further, technically, this is the b of p function, okay? The reason we don't leave it this way is just because it's more trouble to plug in x values and things like that. But because of the way it's formed, I have to recognize that I have brought the baggage of p of x from the construction, because p is the inside function. And just look at it. The way it's set up, I've already got the p function here. You can see that if I were to plug in 7 for x, just like the original p function over here, x can't be 7. Right here, same thing. If I let x be 7, division by 0. Not in the big way, right? Not the big, just each little division here. If I let x be 7, each one of these would be undefined by themselves. Okay? So p of x has brought with it already the restriction right here. X can't be 7, period. Okay? So that's the baggage that the inside function has brought with it here. Now we want to simplify this function. Well, the easiest way to simplify a compound fraction, whenever you have fractions inside of fractions, is to multiply by the common denominator in the top and the bottom of the big main fraction. Well, if I look around, I have an x minus 7 denominator, a 1 denominator, an x minus 7, and a 1. So it looks to me like the common denominator is x minus 7. So then, to continue simplifying here, what I'm going to do is multiply x minus 7 times each piece. Like this. See? Now be careful. This is not x minus 7 times x minus 7. Technically, it's over 1 in both of these places. I'm doing it to get rid of these x minus 7s, and it actually works because I'm multiplying and dividing the chunk x minus 7. What that leaves me with is 3x plus 1x minus 7. So this simplifies down to 3x plus 1x, which is 4x, and then 1 times negative 7 is minus 7. In the denominator, I've got 3x plus 2x, which is going to be 5x, and then 2 times negative 7, which is minus 14. Now I can't simplify anything from that because none of them have a common term or in any way, and the fraction is completely reduced at this point, can't factor anything or whatever. So I'm going to leave my b of p function here with the extra knowledge that I already said x can't be 7. Even though, hey, look, 7 will work. You can plug it in, it won't cause any problems. That's not the point. That is not where the function originally came from. This is. Technically, this is the definition of that function. That's just a simplification to make all of our calculations nicer and easier. So I have to remember that x couldn't be 7 in the original definition, and therefore this works everywhere except when x is the 7. When x is 7, it's just undefined. So what's the domain of b of p? Let's answer that first question. Well, x can't be 7. That's one of the domain restrictions. Also, just look at it. It's at this fraction right here. 5x minus 14 can't be equal to 0 either. Right? So I'm going to solve that. 5x minus 14 can't be equal to 0. If I add the 14 and divide by 5, we find out that x can't be 14/5 either. So I have two restrictions for my b of p function here. I can't be 7 and I can't be 14/5. So my domain is going to be x is an element of the intervals from negative infinity up to, wait a minute, make sure you get it right. Which one of these happens first, right? 14 over 5 is going to be something slightly less than 3. And then this is 7. So this one happens first. I'm going negative infinity. What does it hit? It first hits the 14/5. Union with 14/5 to 7. Union with 7 to infinity. So I have those three intervals where I'm cutting out these two numbers, and I can have everything in between them. Now, the next piece, we were talking about how to find b of p of 6. Well, all right, since we have already got a function, that one seems like an easy way, right? Sure. b of p of 6, since I've already got the function, in this case, I can just plug it in, right? That would be 4 times 6 minus 7 over 5 times 6 minus 14. So that would give me 24 minus 7, which is 17. And then 30 minus 14, which is 16. Okay? So I've got that. But I also wanted to show you that there was another way to get these function values. Just like earlier when we were doing the function combinations and we talked about how you could plug it into each one individually and then multiply them or add them or whatever. Something very similar here, but you have to remember I'm not exactly feeding both functions with the same input here. When you have a composition, one of the functions is fed by the x, and then the other function is fed by the first function, or the one that's on the inside. Remember? b of p of x. Remember, the other way that I can represent this is that it's b of p of x. So when you feed in an input, that input x just feeds p in this case. And then whatever the function, the p of x function puts out, b then feeds on. So that it's not exactly give x to both of them and then combine them. That's how the other combinations work, not composition. Composition has to be a shell method or a domino effect. You feed one, and then that one feeds the next one, and then the next one feeds the next one, so on and so on. So this is one way to get that function value, create the function and then plug it in. Or the other way is I could do b of p of 6. In which case what I'd be doing is just plugging 6 into the p function first. Okay, so that would be b of, plugging 6 into the p function would be 3 times 6 over 6 minus 7, which would give me 18 over negative 1, or b of negative 18. Then I would just take the negative 18, right, and feed it into the next one. b of negative 18 would be, from the function up there, negative 18 plus 1 divided by negative 18 plus 2, which would give me negative 17 over negative 16, which is 17 over 16. Notice the same answer, which it should be, right? It's one calculation. So this is two different ways for you to get a function value of a composition. Of course, like any function, create the function, plug in the value is one way. But with a composition, you can also do the domino feeding, right? If I start with the inside function, feed that number in, let that calculation brew, then feed the outer function, right? It's the same thing. That's what compositions actually do. One function then feeding the other like that, okay? So I hope that these have helped you understand the different ways that we combine functions and how to read the symbols and the namings of these particular functions on top of the way that we analyze them.